And then there's some discussion of target material and some sample problems. There's a very important equation on page 123, which I think is plenty simple enough, so that, and it's very useful when you're in practice. So it's basically, it can be it can be derived from what's the I'm really embarrassed now. What's the this is the basic equation, right? Yeah. Okay. You can actually derive this useful little equation that I'm going to write down, from first principles if you make the appropriate substitutions. But a useful equation just to remember, in everyday life is this one here, where E, the 12.4 is appropriate for when E is in kilo electron volts, like it always is in clinical diagnostic imaging, and lambda is in angstroms. So, for instance, you can see that for a 1 keV for a 1 keV photon, the wavelength would be 12.4 angstroms. Okay, so that's a very long wavelength for X-rays. As a matter of fact, we couldn't image any object more than a few microns thick with 1 keV. But for a 10 keV photon, lambda would be equal to 1.24 angstroms. Okay, so a 10 keV photon has 1.24 angstroms, so it's about 1 angstrom. And a 100 keV photon, lambda would be equal to about a tenth, or 0.124 angstroms. Okay, so that's the range of wavelengths that we're talking about, is about 1/10 of an angstrom to 1 angstrom in clinical medicine. And for some of the more exotic scientific stuff that I'll show you, where we try to use very low energies, less than 10 keV, then we might be talking about several angstroms. And there's a very interesting band of wavelengths for biological microscopy, X-ray microscopy, which happens to be between 22 and 44 angstroms. So these are very, very low energy X-rays, about 200 to 500 EV. And I'll mention later on this week, maybe we'll get to it today, why the 22 to 44 angstrom wavelength region is very, very interesting in biology. But someone asked me, I guess I'll finish going through this handout, just an overview of what's there. And then basically I cut it short after a discussion of the focal spot, so there's a little discussion of the Heel effect and the angled anode, and what effect that has. The source size equals, the sine of the anode angle times the height of the electron impacted area. Then the next chapter that I have some excerpts from is this influences on image quality. And there's some very nice diagrams that we'll try to address a little bit more, where they take the form of these kind of charts where you have image clarity and the first one in the middle. And then these boxes, or these ovals with the arrows pointing in, are the major determinants of image quality. So contrast and unsharpness, which we talked about, distortion and artifacts and noise. These are all things that we'll be addressing a little bit this week. And then he breaks it down for the case of unsharpness. He has these sub-contributing factors to that. And the one we talked about was this geometric unsharpness due to the finite size of the focal spot. And then these other ones are very intuitive, like motion unsharpness. If your object moves while you're taking your image, you're going to have a problem because it's going to blur the image. Receptor unsharpness is something that we'll get into in some detail. It's basically the properties of your detector system. And as we'll see, most detectors have to convert the X-rays into an intermediate lower energy form, usually visible light. And in the process of doing that, there's a lot of, the visible light tends to spread out. So an ideal point would become a little area. And so there's another source of image blurring. Subject unsharpness is he gives a little diagram of it a few pages further on. It's just this concept of, when your subject doesn't line up exactly with the straight lines of the X-ray beam, instead of getting a perfect step function, you're going to get a gradual rise in the signal. So that's it's a very trivial effect. I mean, it's very intuitive. If you just thought about it, you'd realize that it was there. Then he has a similar diagram for contrast. And we'll be talking a little bit about that. And then the very important one for image noise, and we'll talk a little bit later about some of these contributors, structure noise, radiation noise, receptor noise, and quantum model. Those are all very important effects. And noise it's a constant battle between signal and noise is really the dynamic tension that makes imaging so interesting. You're always trying to battle against noise. And then he talks a bit about each of these types of noise. And then the last chapter is basically quality control types of things to maximize the image quality. And we're going to talk, I included that mainly because of the section starting on page 455, or actually just before that, on page 453, where it starts talking about contrast response. There's a very nice little discussion of the modulation transfer function that we're going to talk about now. And it's a fundamental concept about image quality and resolution that some of you are probably very familiar with. You may have even measured it for some systems, and others, maybe you never heard of it. Have you ever heard of modulation transfer function? It's fine. I mean, it's an imaging thing. But it's a fundamental imaging thing, so we'll try to shed some light on it, or explain it a little bit, and how we measure it. And also, I really like these charts on page 458 and 459 of kind of following the quanta through an imaging system, and we'll talk a little bit about those diagrams. So someone asked me a question over the break, and I'm very glad they did, because one of the main reasons I wanted to talk about these physical effects and that model of the atom had to do with this concept called K-edges. And you've seen it in a number of the graphs that we drew. But basically, when you plot the attenuation coefficient, which now we know is a combination of the photoelectric and Compton cross-sections, it always, for any element, it's going to look like this. And what these sharp discontinuities are, where you see a very markedly increased likelihood of an event or an absorption happening, are called K-edges. Okay, so these things here are K-edges. And because this plot here is usually a logarithmic one, these are very dramatic. They can as you go from this side of the K-edge and go to higher energy, and just when you hit the K-edge, you can go up an order of magnitude or more in your likelihood of an event or an absorption. So they're very important. And the reason that they occur is that for every element, we talked about the photoelectric effect ejecting a K or an L shell electron from the atom. And I don't know how to explain it except just saying that it's a simple law of physics that whenever you have an energy exactly equal to or just greater than the binding energy of a K or an L or an M electron, you have a dramatically increased likelihood of a photoelectric event. Okay, so this would be the way I drew it for most of the atoms that we're interested in, this would be the L binding energy. So this here would be equal to the binding energy of the L shell. And this energy here would be equal to the binding energy of the K shell for whatever atom. Okay, so these binding energies are a function of Z number, but you can look them up in the CRC, you know, the Handbook of Chemistry and Physics, or any number of sources will tabulate these binding energies. So getting back to a little discussion we had yesterday about the radioactive, the radioisotope X-ray source, or gamma ray sources, one of the reasons that they're so nice, and one of the reasons that we try to kind of shape the X-ray spectrum of laboratory sources to make them quasi-monochromatic, or at least enhance the radiation emission in a certain energy bands, is because if you think about it, if we had, for instance, let's say that these were the K edges for iodine. Okay. So, and actually, obviously I'm using K edges loosely because the most important edge is the K edge. This is strictly this is a K edge, and this would be an L edge. But no one ever talks about L edges. You just call them all K edges. But in the case of iodine, this binding energy here is about 33 keV. I think if I'm not making a drastic mistake, it's around that energy. So if we had a body with blood vessels in it, and we wanted to image the vasculature, okay? And so we were able to inject iodine into the bloodstream. So we'd have a low but significant concentration of iodine in the blood. And if we were able to take one image with a monochromatic spectrum at an energy just above the K edge of iodine, we would get very heavy absorption of these X-rays by the iodine. And then if we were able to take a second image without the patient moving, just below, you know, and again with a monochromatic source, but just on the other side of the K edge, we'd have a much, maybe 100-fold less likelihood of an interaction. So in this image, the iodine vessels would absorb very strongly, and in this image, they would absorb much less strongly. But because these energies are so close, all the other tissues in the body, including bone and liver and all the other things that had no iodine, would absorb almost exactly the same, right? So then if we were able to subtract, you know, the low energy image on the below the K edge from the high energy image where the iodine absorbs strongly, we'd get rid of everything. Everything in the image would almost go away except for the iodine. Okay, so we would just have a very dramatically enhanced contrast of the blood vessels. And that's the whole concept behind what's sometimes called energy selective imaging, or it is the concept behind digital subtraction angiography, where you try to enhance the absorption of the object you're trying to see by the addition of some contrast agent, or maybe in research, oftentimes you have objects that just naturally contain an element whose K edge you can exploit for imaging. So since we're not blessed with monochromatic sources for the most part, unless we use a radioisotope source and we can find the right radioisotope with these two energies, but mostly we're confined to laboratory sources, which we've seen have this broad Bremsstrahlung spectrum of X-rays. So what we'd like to do is somehow filter the spectrum to alter it and enhance the radiation in a certain wavelength region. So let me see the best way to explain this and keep from confusing myself and you. So we have this, we don't have monochromatic radiation, but we have a spectrum that may look like this. Now, so what we want to do is try to enhance the radiation around some chosen energy. So what we could do, the easiest thing to do is to put a filter in the beam that consists of iodine. Okay? So if you think about it, if we put a filter in the beam that consists of iodine, it's going to preferentially absorb, it's going to absorb more X-rays just above the K edge. So we're going to have an enhanced emission relative to the original spectrum just below the K edge, right? So it might change this, the spectrum might be altered to, I'm not a very good artist, and don't take the exact form of these spectra seriously, but so it's going to absorb more strongly here. Let's see what that. It's going to reduce all of this somewhat, but it's going to mostly make a dent in the spectrum here. So if we filter this beam like this, now we've succeeded in getting a beam that has more radiation just below the iodine K edge, so that even if we took one image with this filtered spectrum, and we just took another image with this original blue spectrum and subtracted them, we would increase the contrast of iodine, relative to a single shot. But especially if we lived in a perfect world and we had infinite flux, which we never do. I mean, the problem with this filtering approach is that if you try to get too smart and play too many tricks and put all kinds of different filters in the beam, then you end up with no beam and no photons. So you can't do too much of this. But what you might want to do then is look in the periodic table, and I have a slide that illustrates this, but it's easy to look in the periodic table or listing of these K edges, and you'd like to find another element to use in your filter that had a K edge just lower than the K edge of iodine, okay? And so then it would be even better than what I just described, which was just subtracting an image taken with this iodine filter to one taken without it. You'd get an even better image if you were able to take an image with this iodine filter and then one with a different filter whose K edge was just below here, okay? So that would even enhance the difference more. So this is one concept behind chemically sensitive imaging that a lot of people try to exploit. And usually it's done just in the form of taking two images, one without a contrast agent. Okay, so you take an image of the patient before you inject the iodine, and then you take an image of the patient, or many images of the patient, while the iodine is in the bloodstream, and you subtract one from the other. So that's exploiting the fact that some images have the contrast and others don't. But in research, you can get even fancier and start to do these things with filtering the spectrum to really dramatically increase your contrast. Unfortunately, at the price of flux. You lose a lot of X-rays when you start throwing filters in the beam. Because if you throw a very thin filter in the beam, a very thin filter is just going to have very little effect. It's just going to do that. So you want to put a thicker and thicker, in a very thick filter. Well, actually, what a very thick filter would do, would be this, and this is the whole problem. You lose all this energy in here for imaging. So there's some compromise between how thick a filter you put in and whether it has any, whether it does you any use. So that's the K-edge concept, and I guess I should mention one more thing, and I won't even try to draw a picture, but you might imagine how you could get even smarter, because these K-edges, okay, because of the fact that you have an enhanced chance of absorption at a K-edge, you also have an enhanced chance of characteristic emission from the anode, okay? So you might want to remember your anode Z number determines the location of these enhanced K lines in the spectrum because of this exactly the same phenomenon. You're having an increased likelihood of electrons undergoing that characteristic interaction where they knock out an inner shell electron and you get this characteristic radiation. This is a function of Z number. So you could try to pick a target for one image that produced X-rays, you know, above and below the k-edge of whatever your contrast was. Okay, so you might pick copper for one exposure. I don't know if these are the right elements, but you might, if you had a research situation where you could change the anode in your tube, like we can, you might take one exposure with a copper anode, and you might take another exposure with a silver anode. And then you could think of you could look in the periodic table and pick an appropriate contrast agent, you know, whose k-edge fell between those two. And then, you know, you could complicate the experiment by also using filters. So there's quite a bit you can do if you have control over your anode material and your filter material. Okay, so now I wanted to, before talking about noise and some of the things in this handout, I wanted to say a little bit about detectors, because the image, that's really, you know, X-ray sources, if you ignore the development of synchrotrons and laser-produced plasma sources, haven't changed much since, you know, Wilhelm Conrad Röntgen in 1895. All the X-ray sources have been based on this concept of blasting a target with electrons and getting Bremsstrahlung and characteristic radiation. So the sources are not really a very active front of research, except for a very few groups who have access to synchrotrons. Did you say anything about the synchrotron in your introduction? No. You know, as you all may or may not be aware, there is a synchrotron in Brazil, in Campinas.
No, I said this.
Oh, you said it? Okay. Okay. So, you know, one of the reasons that I continue to, besides the fact that I like him so much, one of the reasons that I continue to stay in contact with Marcos is this connection with the Brazilian synchrotron. And you know, it's our hope to exploit the monochromatic energies and the very, very high fluence or the very, very intense radiation at the synchrotron to do some high resolution micro imaging. But much more active in terms of the number of research groups pursuing you know, technological advances is the area of detector technology. And that's come a long way. While film and film screen systems that we'll describe here you know, dominated all the way, I'd say, well into the 70s, and they still dominate today. But starting in the 70s with the development of solid-state materials and the dramatically decreasing cost of computing power, digital X-ray detectors as alternatives to film have just you know, become very, very important. And almost anyone will agree that the future of radiology and imaging in general is going to be almost completely digital. Film as a medium is going away much more slowly than people predicted in 1980. There were people in 1980 saying that all of radiology would be filmless by 1990. And here we are in 1999, and over 90% of all image data collected in the world is still collected on film. So it's happening slowly because technology, the demands on technology for computing speed and even more importantly transmission speed, bandwidth on the networks, the demands are so intense from radiology. I mean, these images contain, you know, tens of megabytes for some studies, hundreds of megabytes for other studies, so that, you know, in the course of a day, an average radiology department would produce many terabytes of information. So it's obvious that that's very challenging to, if you've ever sat at your computer surfing the World Wide Wait, you know, waiting for a file to come across, you know, the radiologists don't tolerate that very well. So. So, you know, the film screen systems that dominated, you have X-ray film, which is usually a polyacetate or a polyester support layer. Okay, this is nothing but a vehicle to support the emulsion, and then there'll be at least one side of this thing will be coated with what's called an emulsion. The same as film that you use in your camera. And this emulsion will contain grains of usually always a silver halide, usually a silver bromide doped with iodine. And these little crystals in a binder, they'll be like a gelatin binder to hold all the little crystals together. But due to the doping of the silver bromide crystals with iodine, they are photosensitive, okay? And I won't go into the mechanisms of latent image formation and film processing because that's not necessary for this course. But they're light sensitive and they're also X-ray sensitive. But the problem is, even though these silver, okay, so I guess I'll write that down. The active ingredient in the emulsion is always a silver halide and usually silver bromide, and just take it from me that it's photosensitive. So you could shine the X-rays in here, and if they interacted with a crystal, you would get image formation. But the problem is that I don't even know exactly how thick these emulsions are, but they're on the order of maybe 10 to 100 microns thick. And if you looked up their density and calculated their average Z number and put them into that equation that we had excuse me, for the photoelectric and Compton effects, you would find out that almost no X-rays above a few keV would be absorbed in a layer this thin. Okay, so what's done about that is that it's helped a little bit by putting an emulsion on both sides of the film, which is usually done. So here'd be another emulsion, but still that wouldn't stop many X-rays either. So then what they do is they put the reason you talk about film screen systems is that you put a screen at least on one side, and almost always on both sides of the film. And I meant to draw this one. The top screen is thinner, and the bottom screen is thicker. So these screens would be thicker than the emulsion, and they would be filled with a phosphor. Okay, so these are phosphor screens. Okay, they contain particles of phosphor. And the way these phosphors work is they absorb X-rays, and in response to it, they give off visible light. Okay, so these phosphor particles exhibit the property of photoluminescence. Okay, so they absorb X-rays and they give off light. And the most popular phosphors, because of the fact that they're readily manufactured and they're dense, okay, so they have densities around 9 or 10 grams per cc, happen to emit in the green, so they emit green light in response to X-rays, and a few of them emit blue in response to the X-rays. It's just a physical property of the elements in the phosphor. So then what happens is you get much more X-rays being absorbed and giving off visible light, which then goes on, and because visible light, green, blue to green is 2 to 3 EV now. Okay, so these are very low energy, and they will almost all get absorbed in the emulsion. And so, but if an X-ray doesn't get stopped in the front screen, it might get stopped in the film, very, very rarely. But then the higher energy X-rays might get stopped in the back screen and go off to expose this emulsion. So there's a big science, companies like Kodak and I don't know who, do they function in Brazil also, Kodak and DuPont? There's a multi-billion-dollar market developing and selling these screens and film systems, and for every kind of exam there's going to be a different film screen system, optimized mainly by, you can have a thin front screen and a fine emulsion on the front to try to stop the low energy X-rays and give high frequency or fine detail into the image. And then the idea behind this one here is that it'll stop the higher energy X-rays and stop more X-rays and give the kind of low frequency gross variation of attenuation in the patient. And so often this back screen will be thicker and this one will be thinner. So this one would optimize the fine detail, and this one would optimize the low frequency, but get lots of exposure. So, and I'd like to talk a little bit about why a thin screen optimizes fine detail. And it's pretty easy to do, but maybe I should blow it up a bit more. If we make a picture of the screen where it's a little bit thicker, and you imagine an X-ray which experiences an interaction right here, okay, this normally would give off light in all directions. Okay, so only half of the light would even be headed in the direction of the film. And the problem is that the information carried by this X photon had to do with something in the object that, hopefully if it was a photoelectric event anyway, was in line or occurred at this point. But the problem is with this what's called lateral spread of the light in the screen is that it's going to go off and expose the emulsion over a distance here, okay? So if you, for instance, had the image of an infinitesimal point object that was contributing here at this location in the screen, and if I draw the image upside down here, you would hope your image would just be a delta function at that location. But because of the spreading of light, what your image in fact looks like is going to be some kind of a Gaussian thing like this, which in a minute we'll start calling things like point spread function. But an event that happens far away from the film, this is going to be broader. If you had an X-ray that interacted down here, again, the light would go in all directions, but it doesn't have as much distance to spread in, okay? So here, instead of a delta function, you'd get a much narrower thing. And since X-rays are interacting at all depths in the screen, you kind of get this general blurring of the image. And the rule of thumb, you know what I mean by rule of thumb? Does that make sense? A simple way to think of it without getting into any big equations is that the lateral spreading of this light degrades the image resolution by an amount equal to the screen thickness. Okay, so if these screens are usually on the order of 100 to 500 microns thick. So, this spreading of the light here would be on that same order, 100 to 500 microns. So there's all kinds of things that they do at Kodak and DuPont to try to help this. The most common thing you do is you add a black opaque powder to the binder around the phosphor. So the black powder will absorb light and keep it from going a great distance in the screen. Another thing that they almost always do is they put a reflective layer. This is not so much to combat spreading, it actually makes the spreading worse, but they'll often put a reflective layer of aluminum so that the light that goes in that direction will be reflected back down. So this actually, it increases your efficiency, but it hurts your spreading because this light can move even further. But you can do trade-offs between screen thickness, reflective layer, and black powder. There's a technical name for these black powders, but they're opacifying agents. So this is what the science of screen manufacture is all about. So just to give you an idea about the efficiency, a really good screen will stop about 80% of the X-rays, a good screen system. So the combination of this whole sandwich here, if it's thick, will stop maybe 80% of the X-rays. So the efficiency of basically X-ray to image information conversion, there's a number of factors involved, but one is that you only stop about 80% of your X-rays. And then a very good phosphor has 13% conversion efficiency, okay? So this stopping power it's a synonym for absorption efficiency. It'll absorb this many. But just because an X-ray gets absorbed in a phosphor doesn't mean that it will necessarily get converted to light. As a matter of fact, a very good phosphor only converts 13% to light. So at best you're going to have a conversion efficiency here of 0.13. And then, if you ignore the reflective layer, only half of that light has any chance of going to the film. So there's another factor of 0.5. And even with a reflective layer, because you add these black powders and you have self-absorption of the light in the screen, that factor is never greater than 0.5, usually quite a bit less than 0.5. So if you multiply these out, you're way under 10% in terms of converting X-ray energy to image information. So this is a problem with all detection systems, including film, and it's a very inefficient kind of proposition. One other thing I'd like to say about film, because two other things, but they're both embodied in the same graph, is this kind of input-output relationship, which in the case of film is called the H&D curve. And this stands for the names of two Germans, Hörfeld and Dritter or something. It took me a long time to find that out, but you just call them H&D curves. So this here would be the optical density, which most people call OD.
This is about the exposure curve.
Right. And this here would be the log relative exposure, like you said. What did you have another name for the curve, or you just?
No, it's D curve.
Yeah. Okay, so the way these curves look, basically what this is the input, and this is the output on your film. Okay, so as you increase your X-ray exposure going this way, at first nothing will happen, nothing will happen, nothing will happen. Then all of a sudden you'll reach a region where something does happen, and then you'll level off and nothing will happen again. And very, very strangely and non-intuitively, actually these curves fall at a certain point, but you never get into that region. So what this means is that as you crank your X-rays up or increase your exposure time, you'll get to a point where you start to expose the film, and as you go this way, the film is getting darker and darker. And there's some conflict in the text about this, but usually the useful OD range is from about 0.1 to 5 at most. Some books will tell you 5, but really beyond an optical density of about 3, the film is effectively completely black. So film darkening happens in this range. 3 is almost completely black. And I might as well OD. If you have your film here and you put it on a light box, so you shine light through here, and this light has an intensity of I0, and the light coming through the film has an intensity of IT for the transmitted light. So OD equals log to the base 10 of IT over I0. That's the definition of optical density. So it will increase the more maybe I have this. I think I have this backwards. No, wait. I have this upside down, right? Because if less light comes through, the optical density is bigger. So I think this needs to go the other way around. Right? So now, the less light that comes through, the bigger the optical density, because this is black. And this here is totally translucent. Okay. So where you want to expose your film is in this linear region here. And the slope of the kind of slope of the central portion of this linear region, or almost linear region, is called the is called the gamma of the film. Okay? And so gamma, the slope here, is a measure of contrast. Because this film here has a relatively high contrast. We could have another film whose H&D curve looked like this. Okay. Okay, so this film here has a lower slope, and so it's lower contrast. Okay, it takes a much wider range of exposure, between dark objects and light objects to show the same amount of change in the darkening of the film. So there's a few other things about film. The most important one I want to point out is the fact that these curves are never at zero. Okay, so this level right here is called a fog. And this, along with the nonlinearity of this whole relationship, is really the bad part about film, especially for scientific purposes. Because this fog here is noise. In other words, you could take the film out of the box in a dark room and put it through the processor. It never saw light, it never saw an X-ray, but it would have a non-zero optical density. Okay, if you put it on a light box, it would not look like a piece of glass. It would have this kind of faint bluish haze. Okay, and that's noise. It's a lower limit on your dynamic range that basically kills the dynamic range of film. So I realize that a lot of you don't know at this point what dynamic range is, and we'll get into it a bit later, but basically the dynamic range of film is about 300, which is, you can see beautiful images with film, but this is not a high dynamic range. A very high dynamic range is 100,000. A good dynamic range is say from 1,000 to 4,000. But 300 is, it's okay, but it's not very good. And the reason that this is low is because of this noise here. This is noise. Just to give you an idea, dynamic range is basically the maximum signal you can measure over the minimum signal you can measure. So you can't measure any signals below here, so the minimum signal you can measure in film is fairly big compared to zero. And so you have max over min. So if your min is not close to zero, that's going to make this number small. Okay, so I think that's enough about film and optical density, but now I want to talk a bit more about digital detectors, which have a lot in common with film in terms of this phosphor layer. Almost all digital detectors today still utilize a phosphor layer to... sorry, go ahead.
Why not change the motion, not the motion, the phosphor by a scintillator? For example, because the scintillator have an efficiency very, very...
Yes, yeah, certainly the stopping power. You mean like cesium iodide? Or?
Yeah.
Yeah. Well, the stopping power in a cesium iodide scintillator, for instance, can be 100%. Because you can make these crystals long. But the efficiencies aren't that high in terms of conversion to light. I guess they might be as high as 20%. But I really don't know, except maybe for expense, why they don't make crystalline scintillators. What he's talking about, there's some materials, the most popular of which is cesium iodide, which you can grow in single crystal columns. And they have a number of advantages over granular phosphors. These things here we talked about were granular phosphors, and I think I have a slide of them at some point. But they're basically, if you blew them up, they're little granules like this, and the diameters are usually between 5 and 15 microns. And so you can imagine, I told you that these screens are 100 to 500 microns thick, so you can imagine you get a lot of these granules in here. But they are not very dense. They're only 9 grams per cc for a dense one. And they're very irregular, and they have this problem with spreading of light. In contrast, these single crystal cesium iodide I'm not a very good artist, but if the crystals were hexagonal, these crystals can be grown in very long columns like this, and they can be grown in arrays, or they can be arranged in arrays. I told you I couldn't draw very well, but anyway, you get the idea. You can make a whole array of these things, and the advantage is that the diameter of these things can be as small as 6 microns. So this could be as small as 6 microns. And the fact that you have a boundary between columnar crystals means that you have what's called an index of refraction mismatch. So basically, the X-ray would come in here, and somewhere in the crystal it would get absorbed, and it would give off light in all directions. But when the light hits the edge, if you just looked at a cross-section of the crystal, when the light hit the edge of the crystal, it tends to be reflected off because it comes to an index of refraction mismatch. And so it tends to get channeled down and not spread, okay, in the crystal. So 6 microns is very challenging. That's a very small crystal. But even if it was 10 or 20 microns, you can see that that's a lot better, than this 500 microns we talked about. So conceptually, there would be a lot to be gained. And it's fine that you brought that up, because we're going to talk next about image intensifiers, where they do use cesium iodide scintillators on the front end. So conceptually, there's a lot to be gained. Why they don't do it with film, I'm not quite sure. Maybe it's because the expense. One problem with a lot of these crystals, including cesium iodide, and another one is sodium iodide, is that they, and you can correct me if I'm wrong with respect to cesium iodide, but there's this nasty property of some crystals called hygroscopicity, or they're hygroscopic, which means that if you leave them out in the moist room air, they absorb water like crazy, more than a sponge, and they just basically melt. They just turn into garbage. They go opaque, and they lose all their desirable properties. So you have to encase them in a vacuum-tight environment, which adds to the expense. And so there's technical difficulties with making cesium iodide image converters, but I'm really not sure why they're not used with film. I've never heard of them being used with film. So the next, in terms of the history, film was the only detector available, really, or emulsion-coated glass plates were the earliest kinds of detector. And from 1895 till about I think around World War II, so 1940 something. And then they invented image intensifiers, first for night vision, for the military to see things at night. So what an image intensifier, as the name implies, is basically a very high gain imaging element. And unfortunately, I was maybe tomorrow or tonight we'll succeed in getting some of my files over the internet. But we started an FTP at the beginning of this class, and what did it do? It just kind of got interrupted, or it didn't quite make it. So I'll just try to do my best to draw one here. So an image intensifier.
How much time do you need?
For what?
Finish this stuff. After.
Oh, we're already done.
Yeah.
Wow. Wow. Yeah, we should stop.
It's kind of smart.
Cool. Time flies when you're having fun. So we'll start on, we'll just do that next time. So that was 3 hours, huh?
2.5, I think.
You think I'm going too slow?
No.
Okay. Well, have a nice evening, and we'll see you tomorrow. Left off yesterday, I was just going to say a little bit more about detectors other than film. as I mentioned, there's a big motivation now because of the speed of computers and the need to distribute images widely, especially from rural areas, for instance, to major centers where there's experts to interpret the images. There's a big motivation to develop digital means instead of film. Not to mention the fact that once you have a digital image, there's much more you can do with it in terms of enhancing the contrast and automatic or computerized classification of features and so forth. So the first step towards that, as I mentioned, was in World War II. They developed the first generation of image intensifiers for night vision in the battlefield. And then they've evolved continuously ever since, and they're actually, even though they're relatively old technology, they're extremely highly evolved and really amazing devices, although it looks like they'll probably be outmoded before long by some of the other detectors I'll mention. But basically, it's a very high gain element that takes a very dim pattern of X-rays at the input and produces a very, very bright corresponding pattern of visible light at the output. And it does it by a multi-stage process. What I've done, this is basically how the thing looks. They're pretty bulky devices, which is one of the reasons that they want to get rid of them and replace them with these very compact solid-state devices. The one we use is about this big and this big around. So this is fairly close to life size. And on the front, they first have a protective aluminum layer to protect this cesium iodide scintillator here. We were talking yesterday about how you can grow these. What I've tried to indicate here is that these are single crystal, it's an array of single crystal columnar scintillators made out of cesium iodide. This has replaced the earlier scintillators, which were zinc sulfide, cadmium sulfide. It's a much more efficient scintillator, and it has these collimating properties that we mentioned. In other words, the light, once the light gets excited in the crystal, it tends to not spread to adjacent crystals, but reflect right down the fiber. Then after after the X-rays are converted to visible light, and that's a process where, for instance, 100 keV X-ray would produce several thousand 2 to 3 EV light photons. Okay, so there's a huge multiplication right there. Then there's a very inefficient stage where it takes roughly 150 of these light photons incident on the photocathode here. So photocathode means, light to electrons. So it takes about 150 visible light photons to create one electron off the photocathode. So there's some loss there, but you still have more electrons than X-rays. And then these electrons are basically sucked off the photocathode by this very high potential that's placed across the device, usually between 25 and 40,000 volts between the photocathode and the anode, which is right on the output window. And then this output window will be another, usually a granular phosphor. I believe it's P25 or something. I don't remember the exact identity of the phosphor, but it's a very bright emitting granular phosphor. So the main source well, actually there's two sources of gain. One source of gain is just the fact that you've taken a large image. Many devices are 9 inches, kind of a standard diameter. But there's even, in the clinic, there's even bigger ones that go up to, I think, 38 centimeters is the biggest one. So the biggest one I've ever seen was about this big. And they're very expensive, those large ones. They cost about over $60,000. Ours, which is this size, costs about $35,000. But anyway, it takes a large format image on the front, maybe 9 inches, and demagnifies it or minifies it to a small output window, usually about 1 inch. So right there you have a gain that's proportional to the areas, the ratio of the areas. So you'd have 4.5 squared over 1 squared. So that's about whatever that is. I can't do it in my head, but so anyway, there's that gain due to the small area. You're putting all the quanta onto a smaller area. But much more important in most cases is this very high voltage. So the electrons just gain a lot of kinetic energy and produce a lot of light in the output. And one of the things, I don't think we need to go through it, but because it's not key to the class. But in the handout yesterday, on the last page, I mentioned these, they have these quanta diagrams. And you'll see what I'm talking about for an image intensifier, where you get, you have a few X-rays coming in, then you get this huge gain, and then you get many, many light photons. Then the charts dip down. Is this the handout? I'll just show you what page I'm talking about. It's right near the end. I thought. Do you see it? It's these zigzag-looking diagrams. Yeah, that. What page is that? 459. Page 459. So if you look along the top axis, you'll see it's a logarithmic axis. So these any movement to the left or right can be a very significant. But most notably this. Not all the X-rays are absorbed, so you have this slight decrease initially. But then, of those that are absorbed, it's a direct energy conversion. So you take 100 keV, for instance, and divide it by 2. So you get thousands and thousands of visible light photons, which is, you go from roughly 10 to the 5th, or actually maybe 5 times 10 to the 4th, all the way up to, looks like 10 to the 8th. Okay, so that's the huge gain there. And then you have a slight loss in the output phosphor. And then you have a large loss. Here it says entering pupil. But you can think of that, this lens system that I've shown here could be thought of as the pupil. So you do have quite a big loss in terms of what you can capture with the lens. So what I've tried to show here is, in the old days, and even still today, there are just analog optical ways of looking at this light image here. You could project it onto a screen, for instance. But more and more commonly today, this output light is taken by what's called a tandem optics system. So tandem means 2. And so that means you have 2 lenses usually, or 2 sets of lenses. One set here I've tried to indicate is called a collimating lens. And this lens is focused on the output side to infinity. So I'm not good enough to draw the ray paths in here, but the point is that these rays coming out of here are parallel, focused to infinity, which is the reason for having this lens. Because then the requirements on the objective lens of your CCD camera or other video camera, are not so stringent. Because this is focused at infinity, it's much easier to focus the camera and capture that light. So in our case, I think you'll be able to see in some of my pictures, we have a digital CCD camera here, 12 bits, 1024 by 1024, 1,000 pixels squared, and you just can get you get beautiful images compared to some of the non-intensified systems that I'll also mention on the slides. So that's basically, unless there's questions, that's all I wanted to say about image intensifiers. In some of my slides, if you look at these images visually, if you look at images of a brain or fluoroscopic images through any part of the body, they're very pleasing to look at. They're high contrast, great detail, because these devices are so highly perfected. But if you want to do CT, there comes into play one of the weak points of this device, which is there is a marked geometric distortion of the X-ray pattern because of the inability of these focusing optics to properly focus the electrons on the output window. It's a very challenging job to take this huge expanse of electrons and focus them perfectly on the output. So there's a geometric distortion that's referred to as pincushion distortion. And I don't know why it's called pincushion. Do you all know what a pincushion is? It's like I don't think people have them anymore, but my grandmother had one. It's like a ball, or it may look like a tomato, and you stick pins in it to store your needles. And this distortion doesn't look anything like a pincushion, so I don't know why it's called pincushion, but it looks like this. It's characteristically so if this was the output. What I'm trying to draw here is, the center lines are pretty straight, but then on each side of the center lines, you get this increasing curvature. Okay, so this is a rectilinear grid, So the input on this is the output for an input that was, a grid. So this grid would get imaged like this. And I'll show you in the slides how we use a phantom. We use a grid phantom, where we know exactly what the spacing of these bars is, to do a computerized unwarping or correction of the geometric image, or the geometric distortion in the image. Because while it doesn't bother the eye, it bothers the CT algorithm very much, because geometry is very important in CT, so you have to get it perfect. And the other disadvantage besides spatial distortion is noise. Image intensifiers tend to be quite noisy, which limits their dynamic range, or the range between the dimmest signal you can measure and the brightest signal you can measure, for a very similar reason as I mentioned for film, because you have this low noise that never goes away. So the dynamic range of it, actually I wish I knew, I cannot find any reference to what the dynamic range of an image intensifier is. And I'm having a little bit of trouble thinking of how to do an experiment to characterize it. But just from looking at our images, I estimate that our dynamic range might be about 200 to 300, maybe 500 at the highest. So you see that's less than, certainly less than 10 bits, possibly as few as 8 bits of real information that you have there. So some of the other, since I wasn't able to find my diagrams of CCDs, I wanted to just say a few words about them without getting into too much detail. But many modern imagers now, and I don't think this will last very long, but for about a 20-year input, for about a 20-year time window, between maybe 1980, early 80s and early in the next century, CCDs have been very, very popular as digital imaging devices. I believe that in radiology, at least, they're going to be replaced by these large format flat panel arrays, which I'll also show you. But at the moment, they're still kind of state of the art. So CCD stands for charge coupled device, as you probably know. And they started out as a serial register kind of chip in computers. They were used for other purposes on computer boards before they were ever used for imaging. But it turns out that they work very well as imagers. So if I can just kind of draw a schematic. Basically, this is looking at it on edge. They're little chips. A big one is 1 inch square, 2 or 3 centimeters on a side. A very big one would be 5 centimeters on a side. So a CCD chip that big would be huge and very, very expensive. But they usually have a what's called a 3-phase structure. So these are electrodes on the surface of the silicon. So you have, this is the bulk silicon down here, and there's usually a silicon oxide. Is it O2? Whatever silicon oxide is, there's an insulating layer on the top. And then you have this repetitive pattern of what's called gates, or electrodes. And they're often referred to as Phi1, Phi2, and Phi3. And then it would repeat, Phi1. It's always in a 3-phase device, which is the most popular. Each pixel has 3 gates over it. So a pixel would go from here to here. And what happens is that when visible light or any kind of photons that have more than 1 or 2 eV come into silicon, they have the ability to produce electron-hole pairs. And so you have these electrons and positive electrons available in the silicon crystal. This is crystalline silicon, unlike the amorphous silicon that I'm going to talk about later in the big panels. And so basically, you have electrons being generated in the silicon. And then, without going into too much detail, you sequentially put a higher voltage first on gate 1, then on gate 2, and then on gate 3. And what that does is it creates this thing that's called a potential well under the electrode. And the electrons get attracted into it. Okay? And so, you know, the electrons, when you put the voltage high on all the phi1s, okay, first you put it high on all the phi1 lines. And so the electrons nearest to that phi1 will be attracted into this potential well. And same under this one and so forth. Then what you do is you simultaneously increase the voltage on the next gate and start creating a potential well here while you lower the voltage on this one. Okay? And what happens then is, I don't know how you would say, or bucket brigade in Portuguese. But you know, in the old days when they used to put out a fire, they would take buckets and pass them down a line of men, or women, I guess, to put out the fire. And so we call this clocking out the electrons in a bucket brigade fashion, because you take the electrons that were here and you shift them under here, and then you shift them under here. And then you continue to shift them so that you're able to read the image out. Okay, so you expose the device to photons, create an image, optionally close the shutter. It's easier to think about if you close the shutter. And then in bucket brigade fashion, you shift the image out to a serial register over here where which is connected to an output diode, and that allows you to measure the charge under each pixel. Okay, and so that number of electrons, or that charge on the output, would be proportional to the input of photons. So you can develop this electronic image where the bright and dark, or the high numbers, correspond to lots of photons, and the low numbers correspond to low photons. So you can make an image like this. And so CCDs are extremely linear. You know, unlike film, where we saw it had that S-shaped input-output relationship, CCDs are linear over a very large dynamic range, up to 65,000 or 16 bits. So, you know, if you drew the dynamic range, you know, CCDs would be like this, and film would be like this. I mean, I'm trying to show both a nonlinearity and a vastly inferior, much worse dynamic range. You know, where this would be basically input. This is the input exposure, you know, and this is the output signal. So CCDs right now are very popular, probably the best device for two-dimensional X-ray or any other imaging, really. In the future, I believe in the consumer market, and we're already seeing this, you know, a lot of the kind of digital still cameras, consumer cameras now, have CCDs in them. And you know, now the resolutions are getting up over 1,000 by 1,000, and they're getting affordable. You know, couple years ago they were over $1,000. You know, now you can, I think there's one you can get for like $450 now. And so I'm almost thinking of getting one, because then your kids can take hundreds of pictures, and you know, it doesn't cost anything, and you only save the ones you want. But in the consumer market, they're going to be replaced by this other device, also a solid state device, but it's going to be MOS. Okay, so they're going to go from CCDs are CMOS, and someone's an electrical engineer, but I believe that's complementary metal oxide semiconductor, and they're going to turn into MOS devices, which are metal oxide semiconductors, and I have no idea what these mean, but I can tell you that 99.9% of all chips in the world are MOS, and only CCDs, I think, are very, very few chips are CMOS. And this is why CCDs are so expensive. You know, a 1-inch squared CCD can cost, you know, $30,000, $40,000 if it's a good one, and whereas many other chips cost 5 cents, you know, because they make millions of them. I mean, all the factories are geared up. All the Silicon Valley and Japan, and I'm sure your fab labs here in Brazil are geared up for MOS, and so they've figured out now how to make this kind of logic, or this kind of microelectronic material behave like a CCD. It's not quite as good yet. It's still a little noisier, But you are seeing some consumer cameras come out now already with this. And I think soon it'll advance to the point where maybe they could even be used in science. And so CCDs will become dinosaurs and die out, I think. Because in the other market, in the radiology X-ray imaging market, I think they're going to be replaced by these amorphous silicon flat panel arrays. So amorphous silicon flat panel arrays. So, as the name implies, this is an amorphous form of silicon. It doesn't have to be a perfect crystal. So it's very much cheaper, and more importantly, it can be fabricated into huge arrays. I mean, CCDs, it's very challenging to get, you know, silicon wafers, the crystalline silicon wafers, a big one is 300 millimeters. And it's very challenging to get a perfect CCD, you know, big, like an inch or two. Whereas they already have, you know, amorphous silicon X-ray panels that are 14 by 17 inches, the same size as a regular chest film. Okay, so these can be made into very large arrays. And I'm going to, depending on how much time we have this week, I do have some slides that talk about these devices a bit. But they, instead of being based on this 3-electrode kind of system, the charge, electron charge is generated in a very similar way as in a silicon crystal, but the readout is different, involving TFTs, which are thin film transistors. And they're just basically switches. So you have a TFT, a thin film transistor, associated with each pixel. So you collect your electrons and read them out. And there'd be an array of wires in both dimensions, addressing the pixels in an organized way so you can read out a two-dimensional image. So now I want to just put on some detector slides. And I think for the, if I fall on my face, just turn the camera off. I think we have markers for the slide projector. I think it's better back here because we can make it bigger.
Okay, but I can get the.
Can it reach?
Okay.
I don't want to have that same problem we had. Okay. Can it? That's okay. I think that's good. No, it's okay. I'll just go. Okay, so just need this. So this shows actually almost exactly the detectors we've been talking about, except there's a new one in here. But you know, you can imagine that. I mean, this is just like the image intensifier arrangement we talked about, except there's no image intensifier. So if you had a CCD system that was sophisticated enough, in other words, it was so low noise that it could take pictures in starlight, as we'll see in a minute. And for instance, you could take it out at night and take a picture with it without any enhancement or no intensification. You could also just have a phosphor layer and have X-rays come onto the phosphor layer and focus a CCD camera on the phosphor. And you could take a picture like that. And that's a kind of detector that I am personally very interested in, because provided you can afford the CCD, which this becomes a very expensive camera because it has to have very quiet electronics and it usually has to be cooled to have noise that low. But they do exist, and so this is one way to do non-intensified X-ray imaging with a CCD, and we'll see that again in a minute. We'll see this again in a minute. Instead of focusing the light pattern onto the chip with a lens system, you can also take what's called tapered fiber optics. Okay, this is a bundle of glass fibers that demagnifies or minifies the image, because I mentioned that CCDs are usually less than 1 inch or a couple of centimeters in size, and it's very expensive to get one as big as 5 centimeters. And even for something like breast imaging, you need a bigger input than 5 centimeters because the objects are bigger. So you need some means of demagnifying or minifying the size of your image. So that can be done either with lenses or with fiber optics. And then we talked about image intensifiers, which have the benefit of very high gain. And so, whereas with a system like this, you might have X-ray exposure times of many seconds or even minutes. With an image intensifier, you can do 30 frames a second and actually get motion, image the beating heart, for instance, which you could never do with this. So that's the image intensifiers, but they suffer from noise and spatial distortion. And then there's the flat panel arrays that I mentioned that are coming into use now, especially in they haven't really caught on in the States because the resolution is significantly worse than film, the spatial resolution. But in Europe, they're very common already. I don't know if they are here in the clinic. No? Yeah, they will eventually replace film, I think, but they haven't yet because film has resolution on the order of microns, single-digit microns, like 1. So film will never be surpassed for spatial resolution. But it's very hard it's impossible to do that electronically, because if you take 14 by 17 inches and divide that by a micron, you'd have hundreds of thousands of pixels on each side and billions of pixels in the whole device, and there's no display device, there's no computer that can handle that amount of data. So a small pixel in this kind of detector right now is about 50 to 100 microns. So they haven't been accepted yet by the FDA. But I think they will be. Eventually they will be, because computer power will continue to grow. And I think I've talked about sensitivity and spatial resolution quite a bit without stating what they are. And I think over the next couple days, we'll develop a better feeling in terms of a technical definition for sensitivity and spatial resolution. But basically, if you have a weakly absorbing object or objects that are very similar to their background in terms of the X-rays that they attenuate, they're conceptually hard to image. You can't see the thing unless you have a very low noise, sensitive imaging system. So sensitivity means the idea of having the ability to differentiate very small differences in light intensity. Spatial resolution has to do with the concept of being, it's the distance, it's the spacing between closely proximal objects in the image. It's the minimum spacing that two objects can be next to each other and still be imaged distinctly as two and not look like just one. Okay, so if you had two little points, for instance, and you brought them closer and closer together, your imaging system would see them as distinct points, but then as they got very, very close, eventually you wouldn't be able to tell it was 2 points and it would look like one. And when that happens, that's the limit of your spatial resolution. And we'll see some pictures to make that a bit more clear. In terms of what limits your spatial resolution, we already mentioned that in X-ray imaging, it can never be better than your spot size. Okay, so no matter how you set things, oh, I'm sorry, that's not true. It can be better than your spot size in certain geometries, but if you want to use high magnification and put the object close to your source, like we were talking about for microfocal work, then it becomes limited by your spot size. if in the clinic where the patient is far away from the X-ray source and right on the, basically lying on the film, then the spot source, the source size limitation goes away and the detector becomes the limitation. So depending on whether your object is close to the detector or close to the source, that element will limit it. But in our high resolution mode, spot size becomes the limitation. And then the other thing that you can't do anything about in CT is that every reconstruction algorithm, that's these mathematical methods of synthesizing many views of an object into a map of the object's interior, they're never perfect and they always blur the image. They always reduce your spatial resolution. So these things we can't do anything about. But there's some other things that, if you're not careful, might limit your spatial resolution that we can do something about. So we have to engineer them properly. So other things that you want to pay attention to are your conversion layer thickness. That's this business about the thickness of your phosphor, where the light will spread in the phosphor to a diameter roughly equal to the thickness. So if you want high resolution, you have to make very thin phosphors. If you don't have a good light coupling method, either a good lens system, or in fiber optics, it's even more challenging. I mean, fiber optics have a lot of problems in terms of distortions. And so if that's poor, then that might limit your spatial resolution. And then finally, the number of pixels in your CCD and the physical size of your CCD can have an influence. So you always want your CCD to be big with lots of pixels. You want a good light coupling and a thin phosphor for high resolution. So if you really did everything perfectly, and I don't know of anyone in the world who's achieved this in CT, but if you did everything perfectly and you got lucky, I think you should be able to get resolution in this kind of range, with a 1 micron or slightly less than 1 micron source. But it's very, very challenging, so no one's done it. I certainly haven't. This is a little bit of a busy slide and a little bit out of date, but it's a comparison for these different parameters, being sensitivity, dynamic range, noise, pixel size, spatial resolution. And by tomography potential, I mean, would this detector be good for CT? And the cost, it's comparing film to a CCD-based camera, detector system, to a storage phosphor, which are those stimulable phosphor plates I mentioned that I used for my dissertation. So in sensitivity, basically in the slide, red is bad, green is good, and blue is intermediate. So film, as we mentioned, it's very insensitive. First of all, because it doesn't stop very many X-rays, and second of all, because it has that background fog, which will mask very slight differences in gray level. But the CCD is good, and the phosphor plate is excellent. The dynamic range, film is bad. CCDs are good, and storage phosphors are excellent. Noise, film is noisy, it has that fog. Storage phosphors are good. Pixel size in film will never be surpassed. I mean, it can be less than a micron, so the resolution of film I don't think will ever be improved on. Cooled CCDs, a typical pixel size is about, the smallest pixel I've ever heard of is 6 microns, I think. But you don't want them small, because then you have this problem with demagnifying the image too much and you lose all the light. So it's about 25 microns, and in the storage phosphor it's about 100 microns, so that's not very good. And the spatial that's what we did. Oh, the pixel size is related to the spatial resolution by the demagnification factor. So this line is a bit hard to understand, but there's some assumptions built in here. So obviously at 80 micron pixel, if you magnified a small object, 100-fold onto it, then you divide by the 100-fold magnification, and an 80 micron pixel, gives you sub-micron resolution. For tomography, film is bad because you have to put it in a film processor and digitize it and all that. Cooled CCDs are excellent because your phosphor sits there below your X-ray source, as we'll see, and you rotate your sample around, and the CCD never moves. Okay, it sits in one place, and takes all your data, so everything's perfectly registered. Whereas with storage phosphors, you have to expose them and put them in this plate reader, so everything is not automatically registered, and you have to pay very close attention to how accurately you put it in the device and how accurately you know the coordinate system when you put it in the plate reader. And that's why my dissertation images were, the reconstruction was quite poor. So CCDs are really the best for that. Film is cheap. Those plates are cheap if you don't count the plate reader. And CCDs are fairly expensive. Here's an example of the kind of CCD I was dreaming about using for my dissertation, but I never got the 50,000.
Roger,
Yeah.
what is your conclusion regarding that table in terms of detector?
In terms of a two-dimensional detector for micro CT, these cooled, non-intensified CCD-based detectors are the best available today. I think it'll be about 5 years before these amorphous silicon panels achieve the same low noise levels that CCDs currently have. And then they'll be better because they can be made into large formats. So you can magnify small biological objects many, many fold onto them, okay? And detect X-rays directly instead of first converting them to light and then imaging it onto a CCD. A very important point that I forgot to mention when I brought up amorphous silicon panels is that unlike CCDs, which respond very nicely to X-rays, if you shine X-rays onto a CCD, the small percentage that get absorbed in the silicon will create many electron hole pairs, just like visible light, only many more. But the problem is that X-rays destroy the device eventually. CCDs are not radiation hard, as they call it, because they're a crystalline silicon, and it's crystals are perfect crystals, and X-rays rupture the crystal lattice and destroy the CCD. So after a certain number of exposures, if you expose the CCD directly to X-rays, it's dead. So that's why you have to have this phosphor layer and convert it to light. But amorphous silicon is not crystalline, and so it's radiation hard, and you can shine the X-rays directly onto it. And so it's very, very efficient compared to this business of producing and focusing light.
How big is yours?
Our CCD?
Yeah.
Our CCD is 1 inch format.
1 inch.
Yeah. So it's, and so in our input X-ray image, we have a choice on our intensifier between 9 inches, 7 inches, and 5 inches. So the input, you can magnify the specimen to either 5, 7, or 9 inches. And then it gets reduced by the image intensifier to a 1 inch output, and then that gets focused onto the 1 inch CCD. But if we used our 1 inch CCD and got rid of the image intensifier, which is something that I'd like to do, then we'd probably have to, then 5 inches would become a very big screen, because if you want to reduce a 5 inch image to a 1 inch CCD, that's exceedingly inefficient, as I have a slide coming up. It's less than 1% efficient. So you'd lose 99% of your light coming off the phosphor onto your CCD. So right now, CCDs are still the best. But in about 5 years, or that would be my guess, I think these amorphous silicon flat panels will take over. Which is a consideration for us, because if we're going to build a detector system right now, we're going to propose this, I think, a CCD-based detector. But maybe, that guy Igor, the Russian guy, was talking about getting one 3 years ago, so maybe they have one by now. But I think if we wrote the same proposal in a few years, we'd use something else, probably amorphous silicon. So here's a system, just shows you the phosphor layer, some kind of a glass substrate just to support the phosphor, and then a two-lens system. Go ahead.
She's surprised that the cost of the CCD is so expensive. $1,000.
Yeah, this as opposed to a consumer camera, this kind of price range is for what's called a scientific cooled slow scan CCD. And what's different about them is basically the dynamic range or the noise level. In a consumer device, the noise level will be 300 to several thousand electrons per pixel per readout. Okay, so in a consumer device, you have hundreds of electrons of noise. In a cooled, slow-scan scientific CCD now, the noise levels have come down from about 50 electrons per readout a few years ago to 4. So now you can buy a camera for about that much money that has a noise of 4 electrons, per pixel per readout. And this noise is primarily associated, I mentioned you clock the charge out into a serial register, and then you clock it out in the other direction to an output diode. And this noise is primarily associated with the resetting of that output diode every time you read the charge. There's a thermal and other uncertainty. You try to set the output to 0, but there's this much uncertainty about that 0 level in a cheap chip that's not cooled. And it's taken a lot of technology to get it down to here. And so this, to calculate the dynamic range of a CCD, you need to know this other parameter called the full well capacity. That's what's the maximum number of electrons that can be stored in 1 pixel. And a typical number is about 250,000 to 1 million. So you can calculate the maximum achievable dynamic range by taking this saturation charge and dividing by the noise, and that's the dynamic range. Whereas for a consumer device, you'd see the dynamic range would be compromised because of this high noise. And so you pay all the money. I mean, the number one reason this price is so high is because it's a small market. I mean, I don't know how many of these cameras exist in the world. Maybe, definitely less than 10,000, and maybe only a few thousand of these cameras are sold in the whole world. Whereas the consumer camcorders, there's probably 300 million of them in the world. So it's a market thing. It's just like a television. This always amazes me. A television is basically an electron microscope, okay? But an electron microscope costs, as much as $300,000. And a television costs $300. and they're very sophisticated. Televisions have very sophisticated electron optics in them. But because there's hundreds of millions of them sold in the world, they can do it. I've never understood it. I could go on a little bit. I mean, it occurs to me also, like the tape deck that you have at home. If you sat there and went to make a tape deck, you might finish before you die. But you can buy it for $150. So it's all about the market size. Okay, so this is the point I was trying to mention. When you if you assume you have a 1-inch CCD, for instance, and you take an input of 6 inches, a phosphor screen of 6 inches in diameter, which is already quite small, 4, 2, 1.5, and 1 inch, where the phosphor screen is only the same size as the CCD, that means that your lens system, in order to achieve the demagnification, has to have this focal length. And it means that the cone angle subtended by the lens system is this many degrees, and it means that the efficiency is this many %, okay? So you see that even with a very small input phosphor and a large CCD, you only get 10% efficiency in terms of getting that light to the chip. And by the time you have to reduce the size 6 times, you have less than 0.5%. So 99.6% of your light is thrown away. So this is a big problem. Fiber optics, depending on who you believe, are definitely at least twice as efficient, and I've read numbers as high as 10 times more efficient Does anybody know? I really don't know. There's a lot of controversy, or you can read different numbers in the literature between twice as efficient and about 10 times for these tapered fibers. But then they have the problem of spatial distortions and dead fibers, and it's expensive. So here's a fiber optic bundle where you have, basically you just replace the lens systems with the tapered fibers. These are more efficient, maybe 2 to 10 times more efficient, but they have problems with dead fibers because when you have, these are hundreds of thousands of little glass fibers, and the manufacturing process is very tricky. They heat up what's called a boule. So the boule is originally not tapered, it's just parallel. And they heat it up in a furnace and pull the ends apart so that it necks down. So it's very interesting. It's a very interesting process to me. But so they start out with a big bundle of fibers like this, and they heat it up and pull on it, pull the ends apart. And then so it ends up going like this in the furnace. And then you cool it down, and you cut it here, and you polish the faces up, polish it to a mirror, like to a very smooth, and so you have two tapered fiber bundles like this. But especially if the bigger this ratio, like 6 inches to 1 inch, is very, very challenging. It's very hard to. I don't know if they can even achieve this. More typically, it'll be 2 to 1 or 3 to 1 taper. But in this process, sometimes fibers break, or they don't transmit light anymore. So there's problems with this, especially for CT. Okay, so the trade-off when you're designing one of these detectors is sensitivity or efficiency versus spatial resolution. So if you wanted to maximize spatial resolution, you want a thin phosphor lens, a thin phosphor scintillator lens coupled to a chip, because lenses are almost perfect in terms of their geometry if you get a good lens system. But it's very inefficient. It's very unsensitive. So if you want to maximize efficiency at the cost of spatial resolution, then you would want to have a thicker phosphor fiber optically coupled to the chip. So this is it's kind of a busy slide, but what I'm trying to show is 8-bit cameras like consumer devices are, 12-bit such as high-end radiology CCD cameras are right now, and 16-bit, which is the maximum you can buy that I know of in terms of these cooled slow scan CCDs. And down here you have this really should say fluence. This is technically photons per second per millimeter is fluence. And then this should be the fluence on each pixel every second. So you need 10 to the 7th photons per millimeter squared, or 10 to the 4th photons per pixel. And these numbers correspond to this amount of illumination. Okay, so a consumer camera, all of them can function in this, in daylight. But then when it's daybreak or twilight, they can all still function, and at twilight they can all still function. An 8-bit camera, you might, get a very hazy picture, all the way down to moonlight. But you can see that with a almost totally dark night and cloudy starlight, you can still take a picture with these cool slow scan devices because of that very low noise. And this is just this is assuming this saturation charge or full well capacity of 150,000, like that number there. And so the dynamic range of these different devices can be roughly 256 for an 8-bit device, which maxes out your bit depth, 4096 for a 12-bit device, and up to 65,000 for a cooled CCD. 16 bits. This is actually a very useful equation that I always have to remind myself of. What it's trying to show is the trade-off between kind of the geometry of how you set up your specimen imaging. Okay, so this is the magnification of your specimen onto your detector. So that's this geometric magnification because the beam is spreading. And then, so that's kind of your you know, the way you set up your experiment over here. And then over here is the parameters of your camera and your detector. So what you want to do is you want to have this number be small. You want this number to be whatever, 30 microns, 100 microns. And so you can see that matrix means the dimension on your CCD. You know, if it's 512 or 1024, now you can get CCDs all the way up to 4096, 4K by 4K. So that's this number. And this is the size, so if that's big, see, then this equation will get small. Your resolution will get smaller the bigger this is, so that's good. You want a large input diameter on your detector, but we saw the price for that was efficiency in some cases. And then you want you want a low magnification here, you know, to make this denominator, this numerator large. And then over here, there's a kind of a conflict because on the setup side, you would like to have a large magnification, mainly to overcome the spatial resolution of your detector. See, if you magnify your object 100 times onto your detector, your resolution becomes 100 times better than that of the detector, potentially. But anyway, so this is kind of so you want a small specimen so you can magnify it a lot, and a large CCD. And this line pairs per millimeter is the spatial resolution of your phosphor, the limit imposed by that. So this is basically kind of an overview of what's available today. In high-end radiology now, they have 12-bit cameras with 1K by 1K chips or Vidicon tubes, Plumicon tubes. A system that we previously had until we improved our camera to this kind of camera was something closer to a consumer device, a 640 by 480 camera coupled to an image intensifier. And some of the images I have were made with this. And it works, it's okay, because you have the image intensifier. And so you have a very bright light image. But if you want to get rid of the image intensifier, you know, to improve the spatial distortion and the noise, then you have to go to a cooled, this here is supposed to indicate a cooled camera. So these devices both have cooled cameras, and the only difference between them is that this one has a larger phosphor, so that the spatial resolution isn't so bad. So just roughly, I'm saying that the spatial resolution in the clinic is just a little better than a millimeter. If you do everything right with this kind of setup, you might get 100 micron spatial resolution, which is kind of the ballpark that I'm still in. And then if you really built the detectors you'd like, especially for very small specimens, you know, you might be able to get down in the kind of less than 10 micron range. This is just a picture of a very expensive large CCD. It's probably 2048 by 2048, but this is the active surface, and this is what's called a full frame sensor. So all of this is active, photo of active area. And you can't, the electrodes are invisible, but you can see the gate voltages are applied by, from these pins. And one way, something that some people have contemplated for radiological imaging is shown down here, where you would optically couple a large matrix of CCDs. And I've seen one of these where they've used up to 12 CCD cameras, each focused on a different area of a large phosphor converter like this to make the image. This slide is supposed to show that with any kind of columnar crystal or fiber optic scintillator, if the shorter the crystals, or the thinner the conversion layer, the shorter these fibers, you see basically a point source coming in, And this is an indication of the blurring in your image, or the point spread function. So here you notice that it's blurred a lot more than here, because in these long fibers, it's better able to channel the light in a collimated fashion. So you'd like, if possible, you'd like long, deep crystals, but they're very expensive. This is a commercial detector that I was mentioning to you. That I think Igor might have this kind of detector now. This is a big, cool CCD camera back here. This is sold by Siemens for the X-ray diffraction market. And so here's a cool detector, a cool camera, and here's the phosphor screen, and there's a tapered fiber optic bundle, connecting this phosphor screen here. You can see it's covered by a thin layer of aluminum just to protect it, and then there's a fiber optic taking the light back to the CCD. And these are these two-axis goniometers that would have to be switched out on if we used a system like this from Campinas. We'd have to change this part of the device, when we want to do imaging instead of diffraction. This camera, Siemens was selling this about 3 years ago for $250,000. Just the camera. I mean, just the camera plus, the tapered fiber phosphor. This is an example of a prototype amorphous silicon imager from this company called EG&G. And you can see it's the size of this thing. I'm not sure how big this one is, but these active areas now have gotten as big as 14 by 17 inches. So you can image a whole chest on one of these. But they're still a little bit noisy. And the pixels on the commercial versions are about 150 to 200 microns right now. So the matrix is already huge. The matrix on the ones that they're selling in Europe is on the order of 3,000 by 5,000 pixels. So it's a lot of storage requirements for your images. A lot of computer disk space. This shows a parameter that has a big impact on sensitivity, which we haven't defined formally, and I don't think we need to, but it's basically the quantum efficiency. In other words, it's the ratio of the number of quanta, usually photons, incident on the device to the number of quanta actually detected, actually registered as an electronic signal. So you notice that for all these, so we have here we have a photodiode, which is also crystalline silicon, very similar to a CCD but noisier. Here we have a thinned CCD. Here we have a standard CCD that's not thinned. And here we have a amorphous silicon photodiode, which is the new technology. And you can see that silicon responds best to red light, which is in the kind of 600 to 800 nanometer wavelength range. So the response, you usually would like to have a phosphor that emits in the red for maximum efficiency. And then depending on the device, you see it tapers off, and they're not very sensitive in the blue over here, which is a problem for some biological imagers who are using fluorescent dyes and so forth that fluoresce in the blue. They have to do special things to improve that. And it also falls off in the infrared over at beyond 1,000 nanometers. But you can notice that especially for a thin CCD and these photodiode arrays, the efficiencies are quite high, 60 to 80%. But this is for the visible light hitting them. Okay, so then this is diminished by any kind of phosphor conversion layer and lens focusing system or fiber focusing system, so that your final efficiencies in most systems are well under 10%, usually on the order of 1 to 5%. This I don't know why this is in here, except in the area of non-destructive testing, they don't just utilize the diagnostic energy range. This is for 20 MeV photons. For up to this would be what you'd have here would be an electron impact X-ray source, very much like what we talked about, except that the means utilized to blast the X-rays into the anode would be what's called a LINAC, or a linear accelerator. Okay, so this is a massive machine to achieve these huge energies, not just a little X-ray tube. And then what it shows you is that in the body, these CT numbers, or what's also called Hounsfield units that we'll talk more about later, range from -1,000 to 1,000. So bone has the highest CT number in the body, and it's about 1,000. And this is just showing you on this log scale that the reason you need such huge energies is to blast through materials like concrete, titanium, and steel. Okay, these are much denser than the body, so you have to have a whole other technology. And also that has implications on what kind of detector you can use, because these granular phosphor layers won't stop very many 20 MeV photons, so you have to use these columnar crystals at a minimum. And here is a kind of detector that's been used for these very high energy non-destructive testing imaging. This was the one built by Aracor, which is, we were looking at something the other day from them. But they're a custom industrial CT manufacturer. And so here what they did was they tried to get the best of both worlds by depositing a granular phosphor on a grown crystal, a single crystal kind of fibers. So these are scintillating fibers down here, which can be as long as 25 millimeters long. So apparently they have the technology to produce these scintillating fibers, up to 25 millimeters. So that's what you would need to stop, 20 MeV X-rays. But, since you have a broadband spectrum, you might also want to absorb some low energy photons in this phosphor layer, and then the light produced here would just be channeled down the fibers, and any X-rays that got through, might interact. I think this is supposed to show an X-ray interacting in the fiber scintillator, and so I really don't remember how successful this approach went. Okay, so that's that. And now I want to basically shift gears and go back to where we were at the end of the first day to get into the computed tomography aspects. So I have to momentarily switch to the overheads. Yes?
Have you ever heard about the back-eliminated CCD?
CCD?
Some people say that the back-eliminated CCD is better than the forward.
It is. It is. This is a detail that I didn't get into. I don't know if my picture is still up here, but no.
As better as much expensive is.
It's very expensive. It's very expensive because what he's talking about is you notice on that quantum efficiency graph there was a standard CCD which had a peak efficiency in the red of about 30 or 40%. And then there was this thing called a thin CCD, which went all the way up to 80% or more. And so that's all about, and these are only used in science or satellites or, space missions because they're extremely expensive. But, I mentioned that we have these gates or electrodes. And in most inexpensive devices, and even in the kind of $50,000 cameras that I'm talking about, these gates are on the photoactive side. Okay, so your light is coming in this way, and so these gates cannot be metal. They have to be a conductor, but you want them to be translucent, so they don't block all the light. So these are usually made out of polysilicon, which I don't know what it is, but it's a conductor that is partially translucent. It's not completely clear, but it lets the light through. And so if you plot the quantum efficiency of these things, it's not only low, where this would be about 40%. This is detective quantum efficiency. It's not only low, but it has this kind of structure in it because these gates are differentially transparent as a function of wavelength. Okay, so the reason this is because this material absorbs light in different bands of the spectrum. So the fact that it absorbs light at all brings this down And the fact that it's wavelength dependent makes this structured, which is undesirable for some applications. So if you have enough money, what they do is they take this, this wafer and they grind it away. They grind all this material away from the back until they get right up to what's called the photoactive layer. Okay, so they take this wafer, which is already very fragile and thin. You know, I think, does anyone know how thick wafers are? They're less than 1 millimeter. They're very fragile and delicate. I mean, if you drop a silicon wafer, it's probably going to break. And it's a very expensive machine that they grind and polish all that material away until I'm thinking that this is, I don't know how thick this layer is, but I think it's maybe on the order of 50 to 100 microns. It's very, very thin. And so in the process of grinding all this silicon away, most of the wafers get destroyed, and they go into the trash can. And so what's called the yield of these chips is extremely low. And so last time I priced them a 50 millimeter by 50 millimeter front illuminated CCD was about $50,000. And a 50 millimeter by 50 millimeter back illuminated CCD was over $1 million. So it's, you know, yeah, I mean, they have them on this XAFS, you know, which is this space-based X-ray observatory. They use them there. But that's, I think, because, you know, the whole rocket that sends the thing up there probably cost $1 billion, you know, so. Oh, and so and once you do that, this thing starts to look like, you know, it peaks out at over 80%. And this is, you know, red, like 600 nanometers. So they're much better. I wish I could afford one. You know, that number has come down. I think it would be well under $1 million now, but it would be significantly over 100,000, maybe 300,000. Can't remember how close this has to be. Okay, so wait. Okay, should we break now?
15 minutes.
Okay.